everyone. Now I would like to share with you a topic on linear constant coefficient differential equations, LCCDE. Is also one of the subtopic on Fourier transform applications.
Okay, now let me share with you the topic on for the linear constant coefficient differential equations. For the Fourier transform can be used to solve a system functions for LTI system characterized by the LCCDE, which is linear constant coefficient differential equations. So these equations characterized by the LCCDE is like, for example, 2y plus 3yp over dt plus d square yt over dt square equal to dxt over dt. Okay, so if the system, this input and output satisfy the LCC, the linear differential equations, linear constant coefficients, differential equations, so we can directly use the linearity and the convolution properties of the Fourier transform. So for the convolutions, as you know that the y omega equal to input x omega multiplied with the hash omega, and then from the hash omega we can find the from the input and the output we can find the hash omega. So hash omega equal to y omega divided by x omega. Okay, so this is the LCCDE. So let's look at the example. If you have the input xt equal to 3 exponent power negative 3t ut, and the hash t equal to rectangular t over 2, and you have to determine the output. Determine the output response of yt of the system. Okay, so first of all, from the xt, so we know that the x omega equal to 3 over j omega plus 3. Okay, and the hash t. Okay, hash t, you need to know what is rectangular t over 2. Okay, rectangular t over 2, we can find the hash omega. Okay, the Fourier transform of this one. T over 2 is from, by the way. Okay, let's say you don't know rectangular t over 2. So what about rectangular t? Rectangular t is from negative half to positive half, right? Now this is rectangular t. So you also can find what is the lower bound and the upper bound. Let's say lower bound t over 2. Okay, new one is t over 2, right? So t over 2 equal to negative half. T equal to, so you can bring the 2 to the right hand side, and you get negative 1. Then for the upper bound, you can get t over 2 equal to positive half. So this t equal to 1. So this is so-called the rectangular t over 2. It's from negative 1 to 1. Alright. So the hash omega is from negative 1 to 1 exponent power negative j omega t dt. So if you integrate the exponent power negative j omega t, you can get exponent power j omega t divided by minus j omega negative 1 to 1. Okay, so if I rewrite, I can write 1 over minus j omega exponent minus j omega minus exponent minus j omega, positive j omega. Okay. So I would prefer to multiply this negative to this and that, so I can get 1 over positive j omega. Then I have exponent power of j omega minus exponent minus j omega. Okay, so this is the hash omega. Then I want to find y omega. So y omega is what? Y omega is x omega multiplied with hash omega. So from the previous, you know that from the given input, you know that the x omega is 3 over j omega plus 3. Three over j omega plus 3. Then hash omega is this one, 1 over j omega, and then exponent j omega minus exponent minus j omega. Okay, so you can simplify it. Then you can get 3 exponent j omega minus exponent minus j omega. Okay, and then multiply with 1 over j omega plus 3, and then j omega. Okay, so for this part, we can do the partial fraction expansion. Okay, we can do the partial fraction. So since j omega is quite troublesome, so we assume that the s is equal to j omega. Okay, so from here, 1 over s plus 3, then s is can be equivalent to a over s plus 3 plus b over s. Okay, so we move the s plus 3 multiply with s to the right hand side, so we can get a s plus b s plus 3. So when s equal to negative 3, we can substitute in the value. Negative 3a. So a is equal to negative 1 over 3. And then when s equal to 0, so 1 equal to 3b. Okay, so b is 1 over 3. So we substitute the a and b. We can get a is negative 1 over 3. So this is for s plus 1 over s plus 3, plus b is 1 over 3. This is for 1 over s. Okay, and then we already found a and b. We can substitute back the original here. So I write down again the y omega equal to 3 exponent j omega minus exponent minus j omega. And then this one we can write down the value. Okay, so this is 1 over 3, this is 1 over 3, this, so we can factor out with the 1 over 3 here. So I left negative 1 over j omega. So I put back the s to j omega. J omega plus 3 plus 1 over j omega. Okay, what else? So this one, can I simplify? So this one I can simplify. Okay, I can cancel out. So what do I left? Exponent j omega minus exponent minus j omega. And then here I left negative 1 over j omega plus 3 plus 1 over j omega. So now I can multiply in. Okay, I multiply in like this. So I have a negative exponent j omega, and then I have 1 over j omega plus 3, then plus exponent j omega, 1 over j omega, plus, okay, negative is positive, exponent minus j omega, 1 over j omega plus 3, minus exponent minus j omega, 1 over j omega. Okay, so this is the answer for the y omega. So how to get the yt? So for the yt, we can take the inverse Fourier transform. Take the inverse Fourier transform. Okay, so what can I get here? Okay, this part, what can I get? This part, I can use the exponent power of negative at ut. Okay, I can use the Fourier transform pair. Okay, then what about this one? What about this part? This part, I can take the shifting. This one is the time shifting, in which the x t minus t naught, u t minus t naught, then for Fourier transform, this one is exponent minus j omega t naught x omega. That's why if you look at here, if you compare this one with this one, so it is the time shifting. Okay, what about this one? What about this one? For this part, you can have the SGN. Okay, from the Fourier transform pair table, SGNT of this one, you can get 2 over j omega. Okay, what else? Okay, almost done. All right, so we can rewrite it. Okay, for the after taking inverse Fourier transform. So yt, okay, exponent for this one, 1 over j omega plus 3. 1 over j omega plus 3, you can get exponent power of negative 3 tut, right? So this part, you can get exponent negative exponent 3t ut. But don't forget, you have this time shifting. So time shifting is xt minus t naught, ut minus t naught, then you have this one. So you, by referring to the answer of the y omega, you have exponent j omega. Exponent j omega, this means that your t naught is equivalent to negative 1. Then you will get positive j omega. Okay, so this means that the t naught is negative 1. So x, if you inverse, you will get x t minus 1. So it is x t plus 1. Okay, so here I put t plus 1, so t plus 1 here also. Okay, then for the second one, s1 j omega, also the same. Okay, but you look at this one, 1 over j omega. 1 over j omega, if you change to SGNT, you need 2 over j omega. So if you want to use SGNT, you need to fulfill the term format of 2 over j omega. So now is 1 over j omega, 1 over j omega, how to fulfill? So this means that you need to time 2 over 2. So if time 2 over 2, this part this part will fulfill the SGNT. Okay, so for example, SGNT, and then you have left the 2 here, the remaining 2. Okay, then don't forget you have the exponent power of JT. So again, it's the same thing. Exponent power of JT is a shifting of t not equal to -1. So you will get t plus 1. So here is t plus 1. Okay. Then for the third one, 1 over j omega plus 3, you will get exponent -3t ut. Okay, but if you look at here, this is exponent power of -j omega. This means that now the t naught here is 1. The t naught here is 1. So it's t minus 1. Okay, and then minus with this one. 1 over j omega is the same thing just now, is SGN t divided by 2. So if this part is t minus 1. Okay, so this is the answer of the example for the LCCDE. Thank you.